So in the last video we talked about the algebraic properties, and we proved, at least in 2D, we proved some of the properties of these vectors. And let's use these rules then. And I know these rules are, you would have just taken these for granted anyway, and we can see them if we draw them. Remember, when we add vectors together, it's head to tail, and when we subtract them, we're really adding the negative. But let's do some math then with these rules. So we can use these rules to simplify expressions. So here I've got 3 times vector a plus b minus 7 vector a plus vector b minus 2 times vector a and vector b. So in all of these expressions, they're all a's and b's here. Now if they were just regular a's and b's without the vector arrow on top, we could write it as some number of a plus some number of b. Well, that's exactly what we're going to do, but we're going to be just treating them as vectors. Now, just from the fact that we wrote vector a plus vector b, this is in fact a vector. But remember, because we're adding vector a and vector b, they must be the same size. They're both 2D vectors or 3D vectors. They're the same size. So what I'm going to really do then is I'm going to distribute this 3. So let's clean this up here. I'm going to distribute this 3 across that bracket, which is exactly what you would do if they were just like algebra a and b. I still have this minus 7a and 7b. I'm just keeping that. What rule did I use here? Well, I'm using distributing a scalar across a bracket. I'm leaving this piece the same. I'm going to use the same rule. I'm going to distribute this minus 2 across the bracket. Minus 2 times minus 8 plus 16. So now I've got a bunch of a's and a bunch of b's. Let's group together how many a's do I have. I've got 3 here, minus 7 here, that's minus 4. Minus 2, now that's minus 6. So minus 6 of the a vectors. How many b's do I have? 3 plus 1, 4 plus 16 plus 20. So this expression simplifies to be minus 6a plus 20b. Let's check that again. That should be 3b's, 4b's, 16b's. I'm good on the b's. 3b, that's minus 7, that's minus 4, minus another 2, minus 16, yes. So this was a complicated expression simplified down into a linear combination of vector a and vector b. So if I have got vector a and vector b, this expression means go backwards. If vector a goes that way, go backwards 6 vector b's, and then go forwards 20 vector b's, and that will make a triangle, and the resultant answer is this vector. We can also solve equations. So this was just to simplify. We can also solve equations. So here I've got an expression. It's an equation. Left side is equal to right side. And I'm supposed to solve for c in terms of a and b. So what I want is c equals some number times a plus some number times b. So let's clean this up, again using the rules that we kind of take for granted. It's the same method I would do if I was solving for c as just a piece of algebra c. Let's multiply that minus 3 through the bracket like we did before. So that's minus 3a, and that'll be plus 3c when I multiply that through. I still have these pieces. And let's multiply the 4 through that bracket. That'll be 4 minus 32. Now I'm solving for c, so I want to have c equals. Let's see. We can clean this up a little bit, right? I've got minus 3a and minus a, so that's a total of minus 4a. When I combine the a's together on that side. And 2b and 32b. So I can cancel a 2b off each side, or think of me as let's add 32b to each side. That'll cancel this out as 0. I'm using the rule here, a plus minus a is equal to 0 vector. So I'm adding 32b to each side. That'll make this a 34b, and minus 32b plus 32b cancels out. And now let's subtract 3c from each side. So now I've got c equals a linear combination of a's and b's. So yeah, we've expressed c as a linear combination of a's and b's. What does that mean? Well, that means that I don't really need vector c. I can express vector c as a linear combination of vector a and b. So c is a, b, and c are a dependent set. This is a lot of foreshadowing for things that come up later on. We worry about sets of vectors, whether they're independent sets or dependent sets. And in this case, vectors a, b, and c form a dependent set because I can write one as a linear combination of the other. I wrote c as a linear combination of a and b. That also means that I could write a as a linear combination of b and c. Let's just do that. I can write a as a linear combination of, so I'm just dividing everything by -4. If I move this 34b to the other side, that's going to be minus 34b, and then divide it by a -4. Now I've written a as a linear combination of c and b, and likewise you could write b as a linear combination of a and c. They're a dependent set. As long as I can write one as a linear combination of the other. Now this seems like, where's he going with this? Again, I'm laying down some foundation for later sections. That means that I can write them all. Let's move these pieces over, and I can write them as equal to 0. So I can write this as let's take this equation. Let's multiply everything by 4. So this becomes -1, and this becomes 34. Now let's move these pieces, the c and the b, over to the other side. So that'll become minus 34b, and this will become plus c. Now, plus c. Plus c. So, okay, what did I do? It looks like all I did was move everything over to the other side, which I did. I made them equal to 0. What I've written is not right, though. Not yet. What's its problem? Well, I shouldn't just write equals 0. It's not equals 0. It's equals the 0 vector. Now it's good. So we knew we could express, we've had 3 vectors, and we knew we could express one as a linear combination of the other. And as soon as I could do that, I could express A as a linear combination of B and C, B as a linear combination of A and C is a linear combination of A and B. But that means that I can write a constant times A plus a constant times B plus a constant times C equals the 0 vector. So if I can write 1 as a linear combination of the other 2, I can always write it in this form. A constant times A times one vector plus a constant times another vector. So on. That shows me that the vectors A, B, and C are dependent. I can write one as a linear combination of the other. Okay, here's where I'm going with this. A linear combination in general, then, if I can write a vector as a linear combination, the sum of, so the C sub i's are just constants. Up here, if I wrote A as a linear combination of C and B, the first constant is -1/4, the second constant is 34/4. So I've written it as a sum. If I can do that, then I can write one vector as a linear combination of the others. If I can do that, oh wait, there's a little caveat here. If I can do that, assuming that not all the C's are 0, if this was the 0 vector, all the C's could be 0, and then it would always work for the 0 vector. But if I can do that, then the V's form a dependent set. If I need to use all constants of 0 to get the 0 vector, then they are an independent set. All right, but anyway, that's foreshadowing. So here I've got we can write linear combinations of a set of vectors to make another vector. We've got standard basis vectors I, j, and k. So what we mean by I, j, and k I is equal to vector 1, 0, 0, 0. J is equal to 0, 1, 0. And you can see where I'm going with this. K is equal to 0, 0, 1. They're the standard basis. Now they're 3 dimensions, so this is the standard basis in 3 dimensions. And the nice thing about that is I know how long each vector is. They have a magnitude of 1. So vector I goes in the x direction, vector j goes in the y direction, vector k goes in the z direction, and they form a basis. They're all perpendicular to each other. They all form a right angle. They all lie, if I move them to the origin, they all lie on the axis, the xyz axis. And so I can express any vector in 3D as a linear combination of these 3 vectors. And to get the coefficients, how many i's I need, how many j's I need, how many k's I need, is just as simple as reading it off. I need 3 i's minus 2 j's and 7 k's. I need 3 i's minus 2 j's plus 7 k's. So then I've expressed this 3 minus 2, 7 vector as a linear combination of the standard basis vectors, the I, j, k. So that looks really easy. Sure, and that's because these are the standard vectors. So when I write 3 minus 2, 7, you could think of it as I'm giving you the coordinates of the vector when I start at the origin and go to the end of that vector. I'm going to starting at 0, 0, 0 and going to coordinate 3 minus 2, 7. Or you could think of it as when I give you the components of that vector, I'm telling you how many vector i's, how many vector j's, how many vector k's make up that actual vector. It's the same way of thinking about it. Can I make vector 3 minus 2, 7 as a linear combination of these two, 3, 0, 7, and can I do that? Now, maybe I can, or maybe I can't, because I'm trying to make this vector out of only two other vectors. Let's see if I can, though. If I can, that means I should be able to take some number of the first vector plus some number of the second vector, and that linear combination should equal the vector I want. So if I can find A and B numbers that do that. Well, that's giving me, it's actually giving me three equations. If I look at the x coordinate, the first coordinate, that's telling me that 3a plus 0b has to equal 3. That's just looking at the x coordinates. I'm also getting from the y coordinates that 0a plus b has to equal minus 2. And the third equation is 7a plus 7b has to equal 7. So the first equation is from the x components. The second equation is from the y components. And the third equation is from the z components. Now, if you think about equations and unknowns, you can see where I might have a problem here. The top equation tells me that a has to be 1. That's the only solution for the top equation. The bottom equation, no, the middle equation tells me that b equals minus 2. Has to be. If I look at this, so now I know what a and b have to be for the first two equations. That was two equations, two unknowns. I knew that was solvable. In this case, then, since a has to be 1, if I look at the left side of this equation, the left side of this last equation should be 7 times 1 minus 7 times, or 7 times minus 2. That's going to be 7 minus 14, which equals minus 7. And the right side of that equation equals 7. So I can't find one a and b that satisfy all three equations. So try to express this vector as a linear combination of these other two. I can't do it. That means that this vector, the set of all three vectors, must be independent, because I can't make one as a linear combination of the other ones. All right, we're laying down foreshadowing for upcoming ideas. But think about this here. I've got these three equations, two unknowns. 3 equations, 2 unknowns was not solvable. Sometimes they are, if this last equation would have worked. I guess if I would have changed this to a minus 7, it would have worked. So if I would have made this a minus 7, if I've changed this vector to a minus 7, then I could express this 3 minus 2, 7 as a linear combination of these two vectors. Anyway, why do we express things in terms of basis vectors? Well, sometimes it's convenient. Think about these. These are non-standard basis vectors in 2D called the bishop vectors because they, how you would move diagonally on a chessboard. One up, one over. You'd stay always on the white squares, let's say, if you started on the white squares, or one over, one down. So these would keep you, bishops on a chessboard, always on the white squares. And I can express this vector 2, 7 in terms of the bishop vector. So 2, 7 is expressed in regular standard. So I want to express that in terms of the bishop vectors. I want to write two, 7 equals so many times b1 plus so many times b2. Now I know this is going to work because up here this example failed because I had too many equations to satisfy and I couldn't do it with the two variables a and b. But here I'm going to have two equations. The first equation I'm going to have is 2 is equal to a plus b, and the second equation I'm going to have is 7 is equal to a minus b. So two equations, two unknowns, they're two linear equations. I can solve this for a and b. How am I going to solve these? I'm going to take those two equations and I'm going to add them together. If I add, I'm doing elimination here. If I add the 2 and the 7 together, I get 9. If I add the a plus b and the a minus b, the b's cancel and I get 2a. That means that a has to be equal to 4.5. If a is equal to 4.5, then b has to equal to minus 2.5, so that when I go a plus b, I get the 2. So I've got two equations, two unknowns, and I solve for them. That means I can express this 2, 7 vector as a linear combination of the bishop vectors. So if I was always moving in that, why would I want non-standard basis? Let's say we're always moving in a diagonal. We could never move not diagonal. Then it's maybe not convenient to talk about things in terms of standard basis. Maybe we should always just talk about things in the bishop vectors. So I could write 2, 7 in the standard is equal to, I'm supposed to go 4.5 b1s and minus 2.5 b2s. But I want to say that this is in the standard and this is in the bishop vectors. So let's do a subscript that I'm in these special bishop vectors. So I'm telling the reader this 4.5 means 4.5 b1s. This minus 2.5 means minus 2.5 b2s. Whereas the 7 and the 2 means 7 vectors of 1, 0. The 2 means 2 vectors of 1, 0. And the 7 means 7 vectors of 0, 1. We'll mostly stay in the standard basis right now, but just being aware that such other things exist. The last thing we're going to talk about then is the magnitude of a vector. How long is a vector? Well, if I think about a vector, how long is it? I can make a right-angled triangle, and I can use Pythagorean Theorem to figure out how long a vector is. It's basically the distance between 2 points. If I think of a vector as, and we talked about this in the first video, you would get the components of this vector by saying you take the end minus the start, the end x minus the start x, the end y minus the start y, the end z minus the start z, and that would give you the components. If I want the length of this, the magnitude of this, first off, it's always going to be a positive number. Then I'm going to use my distance between 2 points formula that we would have seen showed up on the SAT. You would have saw this in high school. So if I'm talking about a 3D vector, then I'm going to have there's the difference between the x components, where that's this, the end is the 2 and the start is the 1 squared. So I'm just doing distance between 2 points formula. So I'm going to have one of these for x, I'm going to have one of these for y, and I'm going to have one of these for z's. Now the formula I'm writing down is just for 3D. If it was 2D, then I wouldn't have the z's. If it was 4D, then I'd have another extra plus w2 minus w1 all squared. But this is our magnitude of the vector. Oh, and that's done if I have the 2 endpoints. Another way to think about this then is if I have vector A written in terms of components. So if I'm writing vector A as a sub 1, a sub 2, a sub 3, again a 3D vector I'm thinking about, then I can express its magnitude, and this is probably the most common way to do it, as, put commas here, the sum of the squares of the components. So let's do an example and then we'll be done with this video. So we'll grab let's grab one of these vectors. I want to find the magnitude, in other words, how long this vector is. So the magnitude, I'm going to put absolute value bars around that to say the magnitude of this vector. That's going to be equal to big square root the 3 squared plus the minus 2 squared plus the 7 squared. Clean that up. Root 62. That's the magnitude. That's the magnitude of this vector. How could you get a magnitude of 0? Well, it has to be the 0 vector. 0 square, 0 plus 0, or 0, 0, 0 be 0 squared plus 0 squared plus 0 squared. That's the only vector whose magnitude is 0. Everything else will have a positive magnitude.